Well, hello everyone, and welcome to MacDermid Enthone's discussion on the ammonia-free Electroless nickel strike and low metal Electroless nickel systems. My name is Robert Collin. I am the America's Technical Manager and will be the moderator for this event today. The presenters are John Pawlowski, who is the Electroless nickel Product Development Line Manager, as well as Helmut Horsemke, who is the Global Director for Electroless nickel and hard chrome. Please submit your questions as you have them during this webinar. We will be answering most of the questions after this session. If we don't get to your question specifically, we will answer you via email. Again, thank you all for taking time to learn about MacDermid Enthone's ammonia-free Electroless nickel strike and low metal Electroless nickel systems. With that, John, Helmut, the session is all yours.
Okay, great, Rob, I appreciate it. Helmut, I appreciate you joining to help out as well. Unfortunately, I was off on a short-term medical leave, and so Helmut thankfully offered to help me out and present this, and he did such a good job of doing a lot of the beta sites as well for us over in Europe. So it's glad to have Helmut join us from Germany this morning as well. So with that, let's get started, make the best of it. And it's a good news today. The Dow is already up today, so what a great start. So the first thing I want to talk about is our NiKlad ELV ammonia-free strike, and a little bit about the innovation background. Obviously, ammonia, we're all familiar with the smell and the safety and quality and workplace hassles that employees are not very attractive for our workers. So actually I saw a weightlifting gentleman set a record. There was a gentleman over in Europe somewhere for a dead weight record he had set. I think it was 505 kilograms, which is almost 1,100 pounds, which is amazing. But he had quite a dose of the ammonia smelling salt. So it was interesting to see the rush that he got from smelling the ammonia salt. So it just kind of reminded me of what ammonia can do for us when we all get a smell of it. So, and to the point that it's also been banned in the boxing arena. So, just too many boxers that were going back into the ring when they really should have been going to the hospital. So, they actually have been banned from the boxing world. So with that said, it's also a great complexer and chelator. So we know that it helps tie to the nickel atom to metal because it joins so easily, but it also makes it very difficult to break that complex as well to help and cause a lot of our problems in waste treatment and with some of the environmental companies. So the other thing is that CAD and lead free are the ability to get rid of a couple toxics that help as far as meeting the ELV and RoHS requirements and directives. So we like to say that we like to claim, it's hard to claim that it's free. So we always like to make note that it's intentionally not anything added, but just in case there was some very, very minute residuals that are involved. But all of our ELV claims are definitely under the 0.01% by weight, which is the minimum amount of 100 ppm for cadmium. So we have tested a lot of products and they are all meet that requirement easily. So, and another background that we wanted to do is kind of keep practice with some of our best practice products. So with numerous product lines that have come together over the years, from Legacy MacDermid, Legacy Enthone, Legacy OMG, it was really important for us to really maximize our best practice products, consolidate some of our product lines. I know it was a little bit of pain of pruning and rationalization, but it was key to really help so that we could really analyze and see which ones we had truly best systems to come up with best-in-class products moving forward and what we can offer the industry and suppliers. So that's kind of the theory behind the rationalization and pruning. Also, it talks about a little bit about our diversity and what the reasoning behind that was. And then also to differentiate something from us from our competition. I think the competition between suppliers and customers is great. I think that's how we improve our industry and for our customers in general with pushing the envelopes of meeting these directives and regulations and some of the challenges that we run into. But challenges are also opportunities for companies. So that's kind of how we view that. Again, NiKlad ELV AF Strike, obviously ammonia free. So just pretty straightforward of the methodology to the naming of the product. So the function of the EN Strike, obviously it's a thin intermediate layer between the zincate and the final EN product, whether it is low phos, mid phos, high phos for that matter. The strike itself is obviously a mid phos layer, common in the 6 to 9% range. So, but it's acts as an intermediate layer in between what your final deposit is. So with that said, it can help with the appearance of it. Gives you a nice looking layer prior to your final finish, which can help your appearance approval of your final finish as well. So this product here is a little bit less alkaline than some of the traditional systems that are usually kept at usually above a pH of 9. So we'll see, and we'll talk about that later. So this one's a little bit more less alkaline, a little closer more towards neutral, which helps the amount of dissolution of the zinc. So limiting obviously the amount of zinc in the bath and the acidic, the hot electroless nickel baths is important because not everyone has the ability to move baths. So traditional, some jobs will run aluminum to say 4 or 5 MTOs, and then they will move the bath over to another part of the facility or another line where then they can run it out to get their 8, 9, 10 turnovers on steel and whatnot. But not everybody has that ability or capability to do that. It is nice if you have that ability, but not everybody does. So obviously having options of an EN Strike to maximize the solution lives is important for those that don't have that ability. So, and it also helps with the adhesion between the layers and whatnot. So that's important because it is hard to get the same type of adhesion that you can get with other substrates such as mild steels per se. So you can see the chart on the right where it talks about and shows charting how much zinc as far as milligrams per square foot. And obviously you can see in your first zincate is a much looser, grainier deposit, and is obviously going to have significant amount more of the zinc buildup. And then you can see the reasoning behind the second zinc layer of obviously less zincate build, but it's also a thinner, denser layer that is a little more uniform. So that's kind of the reasoning behind a second zincate. And then you can see the final one where it's significantly much more less buildup of the zincate. You can see is significantly low with the EN Strike. So the makeup, it's pretty straightforward. It's pretty simple. You have the B component is your chelation, 10% by volume. The nickel component is the A, like we traditionally label, is also 10% by volume. And then the AF Strike H is the hypo, the reducer, and that is made up of 3% by volume. And then the Strike pH, which is just potassium carbonate, is at 0.05% by volume, just on makeup to adjust the pH to get it in range. So it's pretty straightforward makeup, pretty similar to traditional systems. So the replenishment of the system, the ratio of the part A to part H and pH is, you can see the ratios. So the part A is 10% by volume, and that would be per MTO basically for the replenishment. And then the part H is 3.2% by volume. And the part H again, or the pH again, I'm sorry, the carbonate is 1.5% by volume. So, and there's just a basic chart of additions on typical what you see on technical bulletins as well. So some of the conditions and parameters, this bath runs at 5.4 gram per liter would be 100% activity, and the hypo, the reducer, is 21.5 gram per liter for activity. The temperature is a little higher than maybe some of the traditional systems you might see that we would call this a low temp process versus a room temp. But I get I try to tend away from staying room temp for people, depending on your industry. Myself, I'm in Michigan, so room temp in Michigan could be, 40 or 50 degree rinse water to up to 90 or 100 degree water. So it depends on what part of the area you're at. I think it's important sometimes that to state it as low temp or specific ranges, and sometimes it doesn't hurt to have a small heater or chiller on some units, especially zinc gates per se, that are very, very temperature sensitive. That's key important for the zinc gates as well. As you can see on the pH, it's just slightly less alkaline than some traditional systems where we would probably see some of our other systems or data sheets that we're always usually going to recommend. We like to stay above 9 on those systems. This one is a little more unique the way it's formulated, and has pretty good plating rate of pretty much averaged around 2.5 micron per hour in a lot of the data trial, the beta sites, and we'll see some of that later on in some samples parts as well. So the characteristics, obviously I talked about, is 6 to 9%. All this is pretty common. Here's a note where, like I said, we like to start to make note that no cadmium or lead is intentionally added. So we do make sure we do our part, but it's good to just note it that if there is minor amounts in there that could come from raws that we have no control over. So the sustainability. Obviously, it's a big topic nowadays. It's very important for you guys as applicators and suppliers of your customers and the end users. This is obviously becoming more common where you need to drive down your nickel effluent treatment to reach 0.1 milligram per liter or less. And we talked a little bit earlier about the ammonia is such a good complexer and a chelator that holds onto the nickel that makes it so difficult. So taking this out of the system is obviously going to help meet these requirements and what these future needs are to meet the effluent streams. And then obviously the exposure. There's some customers I know and systems that they just prefer to stay away from. They want ammonia free, they want carbonate systems even for hot and acidic electroless nickel. So some people have just made decisions to stay away from it altogether. And there again, we eliminated a couple of the toxic elements. We think that's very important. We have a few cadmium and lead systems that are still around or specified in, and they are extremely benchmark products as well. But ideally, Helmut and our goal is to make sure we're sustainable as much as possible, and really feel that we have some really good electroless ELV systems that are going to be kind of the future leading our portfolios moving forward. So, and then extending the solution life utilization really helps because it's not just an external saving on external waste, but also internal waste as well. When you're able to extend your metal generations, your life of your system, so you're going to be doing less internal, not only just external treatment or waste that you're sending out. Oh, sorry. So market experience slide. So here's an example. We did an intensive field study that was actually over a year of monitoring it and generating data and monitoring the beta site to the point of customer has continued to use the system after they have tried it. So a couple key things that stick out on this is one of our other previous NiKlad ELV A31 system that is it's a organic stabilized EN Strike. That one only tolerates upwards, I believe, of 500 milligram per liter zinc. So this one is impressive where it was able to tolerate up to 800 milligram per liter of zinc, which is very impressive and looks very promising. So it's good to see that. So it's a definite improvement. And we also noticed that this one had pretty good consistent plating rate, and it was definitely faster than our traditional NiKlad A31 system that we released last year or the previous year as well. So, and obviously no ammonia smell is likable by all at the facility. And there's a picture on the right. You can see some parts, and it was just over 1/10 of a square foot per gallon. So it's on the lower end, but it's good to see that it worked well even on lower end loading as well. So, but this is, we feel is going to be, it's a very stable process and will handle obviously much higher loading as well. So here's just a basic pre-treatment cycle. This ideally wasn't exact products that they had used over in Europe that Helmets Group might have as some of their best practice over there and whatnot. But this is what we kind of are promoting for, especially for our connector industry and whatnot. It's a good cycle that we've come up with for a lot of the 6000, 6061 series that are common. So the IsoPrep 740 is just a non-etch. You can run it at certain levels where you can get a little micro etch, which is kind of nice. And then the Etex aluminum acid etch does well with etching, as far as you can really dial it in and get a nice micro etch, and it's not as aggressive as, say, an alkaline etch. So you got a little wider range on your timing and how long you're in there. So it does very well on a really even, uniform etch. And then the D-Smut, IsoPrep 184, works very well. The key to some of these D-Smuts and whatnot is to make sure you definitely want to have air agitation in the D-Smuts. And then Bondol or aluminum. Bondol, we have two versions. Obviously, Bondol is a benchmark Cadillac process, been in the industry a long time, and we do have a cyanide-free version. And then the Alumon EN has done very well out in the field as well, and seems to tolerate wider temperature ranges than some of the other traditional zincates. So, which is very nice for the aluminum EN. I've been very impressed with that. And then obviously the ammonia-free strike, and then final product, whether it's any NiKlad, Vandaloy, Elmic, end plate, whatever, high FOS, low FOS, mid FOS, etc. It's your final finish. So summary advantages. Obviously, we help improve the adhesion on numerous alloys. Some alloys can be more difficult, obviously. We all understand that one size doesn't fit all in preparation of all the different aluminum alloys and all the alloying elements and how to deal with them and solubilize them to have that surface oxide free to help with adhesion and whatnot. So it helps to have definitely have the advantage of the strike, the EN strike, to help with that adhesion. So obviously, our goal was to meet all our ELV and directives and RoHS, which we're able to meet that by eliminating all the cadmium and lead in the system as well. So obviously minimizing the contamination of the plating solutions that we had talked about and what that can do, and free up some a little bit more opens the window up for the applicator, where they're not having to worry about do they have the ability to move the bath to another line or another tank, or do they not, and not where they don't have to necessarily dump it prematurely when they hit a certain zinc level that starts causing issues with adhesion and whatnot, and need to dump it prematurely and not really get all the efficiency and the life out of the solution. So it's very simple to control, and like I said, we feel it's very stable based on the formulation of the product, and we're excited to see this run more and try and get it out in the field and see what we can do to take it to another level. So with that said, I'm going to switch it over to Helmut. And Helmut, I appreciate you joining and helping.
Yeah, thanks, John. Thanks for presenting. And yeah, this is Helmut Ostemke. I'm dialing in here from Germany right now. So good morning or good evening to everybody from wherever you may be calling in. Yeah, I think it was an important step forward with the AF Strike. Basically the challenge for us was to combine these properties of the very well established and very well proven technologies in the market, but have all these success criteria like being lead-free, cat-free, ammonia-free, to combine that in one process. So we're quite excited about it. But now I would like to speak about NiKlad Eco HP. It's a new low metal high FOS process and John will help me with moving the slides, and maybe you can go for the next one. I would like to give you some background of the innovation. Obviously, when we work with the lower nickel concentration in the end, we can also reduce the concentration of chelators, so reducer, and overall we are reducing the amount of chemistry we need for the makeup to minimize cost, but also to minimize waste treatment, to minimize drag out losses. And we'll go a little bit more into detail with that. We have a long time experience with operating Electroless nickel with as low as 2.5 gram per liter nickel, particularly with the long life EN processes. That worked well, but still overall we saw that it's better to run it with a nickel controller, which is of course always an advantage, but at the same time it is a kind of a complication for technology to establish on the marketplace. We have done it with our steady state system, which was very useful, but the need for this kind of equipment was a limitation, so we wanted to overcome that. Well, why 6 gram per liter nickel as the traditional value? Is just 0.1 mole per liter of nickel. That's where historically, I guess, our colleagues before us had just started to work with and arranged all the other parameters around this nickel concentration, and it was not really questioned very much. So the target here is really to reduce the nickel content without compromise in the mode of operation or in performance. And so this is our motivation for this process. Next slide, please. So I'd like to introduce to you our NiKlad Eco HP. So HP stands for high phos, as a new state-of-the-art low metal high phos EN. Next, please. Here is a brief summary of features and benefit. And as said, the low nickel concentration is mainly to reduce the cost of operation, but it does also have sustainability aspects with reduced work exposure and less losses of nickel. We'll speak about that, and we can use this system as a very cost-attractive continuous operation mode also. As John previously said, cat-free, lead-free is basically a must to comply with all the regulations. So any new process launched should fulfill those requirements, which this process does, of course. We also wanted to stay with a 1-to-1 replenishment ratio, just to keep it simple here. We decided to use a version with add your own pH. So in this way, at the initial introduction phase, we do not need to have both versions for ammonia-free and self-regulating at this stage. So customers, applicators have the choice to use either ammonia or use ammonia-free replenishment option. One key element for high phos Electroless nickel, of course, the plating rate, as high phos is overall plating somewhat slower than other nickel phosphorus alloys, and this is quite important for productivity. Of course, the high plating rate is very relevant for cost of operation. As for the deposit properties, basically, of course, we cannot allow any compromise here for high phos Electroless nickel, and basically we are meeting here the typical requirements for a high phos process, and I think we'll go a little more into detail with the next slide or with the next slides coming up. Here is the makeup of the process. So we have only 3% of the part A, which is equivalent to 3 gram per liter of nickel. And we use the part B at 10% here. And there's one other component that needs to be added. And also, like with many other of our Electroless nickel processes, we have the option to use a very powerful wetter, which can be used particularly for high build-up layers. If agitation may not be perfect, this is very helpful to minimize any porosity on coatings with above a mil or a couple of mils or above 25 micrometers, whatever you want to say. Let's take a look at the replenishment with the next slide. As said, we have a 1-to-1 replenishment ratio. The standard concentration is 3 gram per liter of nickel. we did mention about the ammonia-free replenishment option, and as the solution has a lower nickel concentration, we talk about more than 10 MTOs here, which is comparable to 5 MTO as kind of the typical under low drag out situation bath life that we would expect from a high phos process. The main reason to have some form of limitation in the metal turnovers is to avoid tensile stress in the deposit once the solution ages. It's still operational, but you would see some compromise of the quality. Next slide, please. Yeah, let me speak about sustainability. I mean, everybody is talking about sustainability and it's a bit of a buzzword, but there is something really about it here. And maybe I can highlight a few aspects that are not so obvious. When you consider the solution to have only 50% of the nickel as the main substance of concern in an Electroless nickel process, logically also any airborne emission or exposure, whatever, is minimized by 50%. Whatever we drag out from our solution has only half of the amount of valuable chemistry in it. So in this case, we can use rinses for a longer period of time until they are saturated to a certain point. So that would result in water savings, as well as the savings related to whatever gets lost with drag out. So we need to use less chemicals for effluent treatment, and finally would form less nickel sludge that, depending where you are, would end up in landfill. And of course, also at the end of the solution life, if your concentration is only half of what it would typically be, there is some advantage for concentrate waste treatment that would typically be done externally. John, can you go for the next slide? Here is an overview about the operational conditions of the process. Like as said, it's 3 grams per liter of nickel. The reducer is kept at 20 grams per liter. We have very typical operating range of 185 to 196 Fahrenheit or 85 to 91 Celsius here. So very typical temperature range here. The standard pH towards the beginning is about 5 here from the pH. We are getting a plating rate of at least 10 micrometers here, typically more towards 12, which we'll see a little later on. So 0.4 mil is our conservative approach here. We can operate in a relatively wide range of bath loading. So from pretty low, like 0.1 square feet per gallon to about 1 square feet per gallon. And we have a replenishment ratio of the part D and the part C of 1 to 1. The next slide, please. Yeah, some words about the deposit characteristics, which are critical, of course, for the high phos Electroless nickel as a quality coating, acting as a barrier coating. So we have the typical density range of whatever the number is with the 11% phosphorus content, or a minimum 10.5 here. We have a non-magnetic coating. The hardness values in the as-plated condition, as well as in the heat-treated conditions, are what you would typically expect from a nickel phosphorus alloy of this composition. That's not really so much process specific. It is really a matter of the phosphorus content, and the process is very nicely maintaining a phosphorus content always above 10.5%, which helps to ensure also passing nitric acid test, which is important for some markets. Regarding wear resistance, the coating can be heat treated after plating, and we would get to the typical Tabor wear index numbers that you would expect from a high phos Electroless nickel. And the same applies for electrical resistivity. We also have applied for an IMDS number. So if that should be relevant for your customer base, we have it registered in the European the system for the automotive industry here. Yeah, let me speak a little bit about cost, because low metal, besides sustainability aspect, is really about cost. which is critical for certain application. And it's quite obvious that if you use half the chemistry in the makeup, it does reduce cost. But beyond that, we should also think about any solution that is being lost in operation. And that is not just drag out by the parts, but it's also losses due to filtration. It may be leakage, it may be that tanks are being stripped and they cannot be entirely emptied. So you're always losing some solution here in this way, and the higher those losses are, the more attractive it does become to operate with a no nickel. Obviously, barrel application always has a much higher drag out rate compared to rack plating, but also if the thickness is lower, as you process more surface area per metal turnover in a liter of solution, it becomes more of an issue, the more cost-relevant point. What we've done here is we try to quantify the drag out rate in the process. There are certain ways of measuring that. We would typically say that looking at 1 liter of solution per 1 gram nickel plated, if there is a rate of 0.2%, we would consider that a low drag out rate. So that would apply for cases with relatively high thickness, above 1 mil, above 25 micrometers. And for those applications, potentially oil and gas, bigger components, which are basically rinsed over the tank. So there's really a very small drag out rate. Still, there may be some solution losses with filtration or tank stripping, but that would be considered low. A medium rate of drag out would be considered 0.6%, and that would be the typical market average with rack plating with a thickness of 20 micrometers, or that is 0.8 mil here. High drag out rate would be done when you either plate in barrels or you are plating with a thickness in the range of 3 micrometers, so like 0.1 mil. So then you would see that 1.5 plating rate. I did mention before that basically by a controlled dilution or in steady state mode, if we increase the drag out rate just a little bit above the high number here towards 1.7, that would be equivalent to a steady state operation mode of 10 metal turnovers, which is very realistic for mid-frost. If we would reduce it down to 3.3 MTO, which would be very, very extremely low and probably not affordable, we would need to increase the drag out rate to 5.5%. So this is basically an option here. If a continuous operation is desired, we can artificially increase the drag out a little bit above the level of what you would have with a high drag out rate, and we can basically get to a continuous operation, which would be a very cost-effective option here. Next slide, please. Yeah, well, basically talking about cost, when you consider that typically you have about 20% of your cost is the makeup cost when you run a high frost process where the solution life is somewhat more limited than with the mid frost processes, and you are spending only half the money for the makeup because your process is half the concentration. That would be equivalent to a 10% overall cost saving in operation. We do have cost comparison tools in place, and we're very happy to provide them and to help you populate them. We can simulate the individual situation regarding drag out rates, regarding the process being used in a very transparent manner. We have these tools in metric sizes, but also in imperial sizes. So whatever you prefer, I'm sure your account manager, your salesman is very happy to go through that with you to see how relevant this may be for your application. Again, as said, the higher the drag out is, the lower the thickness is, the higher the cost saving is going to be. We would still expect it to be around 10% in a typical situation due to the lower makeup concentration of the process. Next slide, please, John. Yeah, some experiences from the field here, which is really key. I mean, we test all our electrous nickel processes quite intensively in the field before you take them out. And me and my colleagues here over in Europe, we spent quite a bit of time to make sure that what our R&D colleagues in New Hudson, Michigan have prepared really performs. And this was a very, very good example of a very close cooperation between R&D, tech service, and marketing. Also, we did see a very good stability of the process. There was no need in this case with represervation of the tanks, which is not totally unusual, but still it is something good to know that a lead-free, cat-free, high-phos process is performing in such a way. And we had a very good plating rate over the solution life, and we'll see some numbers on that later on. Also, one key criteria for, I would say, maybe 30% of the market is that the coating passes the nitric acid test in a very reliable manner as kind of an overall test for meeting the phosphorus content and the absence of any contamination in the deposit. This test is still quite common in the market. We can plate many different substrates, rack and barrel application. Both of them have been tested and have performed very well. The coating overall is pretty attractive. I mean, brightness is not necessarily the key feature of a high phos coating. Still, an attractive looking deposit is much welcome on the market, and I would consider this highly attractive for a high phos deposit. What we did find out, and which was a kind of a bit of a surprise to us, is that the thickness distribution in blind holes or in areas on the part which have relatively little solution exchange was substantially better than with a full strength electroless nickel. So if that is anything of interest for you, that may be one additional technical benefit of this technology that you potentially may want to utilize. Of course, we needed to have pore-free EN, high phos EN, also with high thickness, and that was definitely done. One observation from the field was that we should keep the process really at 3 grams per liter nickel. Don't let it drop too much below that. The process still works, but it would slow down quite a bit, and the uniformity, like in the blind holes, would suffer. We would, as we always do with electroless nickel, recommend to use a nickel controller. Still, it can be operated without a nickel controller as long as you keep the concentration in a reasonable range. And on the right hand side, you see some examples here what had been plated, anything from steel and stainless steel, copper and brass, with above loading range here, from very low to medium here, different thicknesses. One example here was we had a filtration of 1 micrometer overflow filtration. We got more than 20 metal turnovers from the solution with electrical heating and pump agitation here in that case. We used anodic protection, and we also tested it without, but just to make sure that the stabilizer system is running fine here and is not causing any issue, particularly when the bath loading, as in this example, is a little bit at the lower end. Next slide, please. Some examples. Usually we do our extensive beta site testing at job shops because they have a wider variety of different components, and we were very thankful for our partners with the beta sites for this serious testing with the part. Here's an example for engineering component with the thickness of 20 micrometers on steel, and the special requirements were the corrosion resistance here, like one of the key elements for high phos electroless nickel. But at the same time, a good level of brightness was appreciated, and particularly stains had to be avoided. Again, some of the components were with blind holes, and they had a very nice and clearly better thickness distribution on the ID areas on the inside of the blind holes compared to the previous technology used. Other examples were more focusing on wear protection, like here on the bottom 2 pictures. Here there was a milder heat treatment after plating to get to an 800 Vickers hardness in this case here. Something that is not so unusual for high P, where you basically want a combination of wear and corrosion resistance for certain engineering components. Next slide, please. We have some graph here about the plating speed. We usually in the bidder sites don't overdo with the test in the initial stages. You can see here plating rate of minimum 10 at the very beginning, but even 12 micrometers, so 0.5 at 6 MTO, still with quite moderate temperature of only 83, 85 degrees Celsius. So previously we said we can operate with 88, so there's still quite a bit of room for temperature increase, even to accelerate the process a little bit more. With a new solution, typically 1 more degree Celsius would increase the plating rate about 1 to 1.5 micrometers towards the end of the solution life. 1 more degree Celsius would enhance the plating rate by 1 micrometer per hour. So we are pretty much on a very much on an attractive level here on the plating rate, with still some reserve, not too aggressive pH or temperature here, and still getting a very, very decent range. The next slide is talking about the chemistry. We were looking at different chelators used here in the system, the hypo content, just to make sure that we can tolerate certain fluctuation of concentration without compromising of the plating rate or the deposit performance. It is very nicely tolerant here to some degree of fluctuation, and you can see that purposely one chelator is building up a little bit over time, while another one is maintained basically at the same level. I think our R&D colleagues have done a very, very good job here, and we had a very good stability, and also concentration changes of the stabilizers were very small, so we consider this very well balanced. John, the next slide, please. I think we will see a summary of the advantages here. We would recommend the process to be operated between 2.8 as the absolute minimum to 3.4 gram per liter nickel. We have some substantial savings potential here, particularly in those cases where we are facing low thickness or high drag-out rate. We have reduced waste, reduced amount of wastewater and exposure. We have a high quality, high P coating with a very attractive appearance that passes nitric acid test. We have a very competitive plating rate here over solution life with about 11 micrometers, with some room upwards, somewhere around 0.4 mil. Very versatile with substrate materials, as well as barrel and rack application. And the surprise here with the blind holes, with a very, very good metal distribution in the blind holes. That is basically what I wanted to share with you regarding the NiKlad Eco HP. And I will hand back to John, who is going to speak about a mid-P process with using the same principles. So some of the elements that I have explained about sustainability, I think we can go through that pretty briefly, John. Would you mind to take over again?
Thank you, Helmut. I appreciate it. And yeah, absolutely. Some of these I will go through very quick because some of it is just obviously it's reiterates what Helmut stressed very well. So this obviously is our Eco MP for mid-FOSS, and Eco, I believe we let it was Joachim Kraft who was heavily involved in the beta sites, and Helmut was generous enough to let him kind of have first choice to label it, and Eco is obviously for eco-friendly. So I thought that was a kind of a good name for these systems as well from Joachim Kraft. So a little bit of the innovation background, as Helmut had talked about a little bit. So the only thing that I might mention to expand on this a little bit is that I think definitely ourselves as legacy companies and even competitors, I think a lot of people have tried and played around a little bit with trying to manipulate their old traditional 6 gram per liter systems and trying to running them as true low metal versions. And we were able to make a lot of them, to some of them work and work well, but they weren't ideal, and there were some lessons learned. So I think the fact that now we have the knowledge and the experience of running traditional systems at lower metal has really helped with our EN team. And as Helmut said, Bob Janik and Nicole Mikas in R&D now really have a lot of the knowledge and ability to formulate these things to truly be run as low metal systems now. So that's kind of unique. But just as a legacy example, in Legacy MacDermid, John Zipka and Bulis Marcos started running low metal over 20 years ago at a customer of ours. So there's a lot of experience we have and a lot of lessons learned of running systems at the lower levels. So I just wanted to mention that and elaborate a little bit on what Helmut had spoke about. So again, it's the Eco MP for mid-FOSS. So obviously it has a lot of the same benefits that Helmut had mentioned before on the previous high FOSS version. So a couple key points that I'll just mention on this one is that it's a single component makeup. So we labeled it a C5, which a lot of our traditional C5 systems are one component makeup at 20% by volume. This one will be at 10. We'll see on the next slide or future slides here. So this is a single component. So this one was able to be formulated a little different than the HP version. And then also we were able to offer pH self-regulating or non-pH self-regulating. So we do have two options as far as replenishments that is a little bit different than the HP system Helmut had spoke about. And they both are replenished at a 1-to-1 ratio, which makes it user-friendly. So here's the makeup. As I said, it's just straightforward, simple. It's 10% by volume of the C5 component, single makeup. So it's as easy as it gets regarding the makeup. So replenishment, as I spoke about, we have MP, HPH, so that will be your self-regulating. A lot of our nomenclature will be when it's HPH, it's always going to be a self-regulating, and when it's just a standard H system, that will be nomenclature for a non-pH self-regulating system where you have the ability to add your own. So it gives people option to add different types of pH adjustments. And not only that, especially for high FOSS that Helmut had spoke about, it does help involve people that really need to dial in their pH and minimum phosphorus contents and plating rate. It really gives them hands-on their own individual adjustment of the pH and how they want to control their system for their customers and what their demand or their needs are. So sustainability slide, Bulis went over this pretty thoroughly and explained this very well. So there's not too much more to add to this one. It's pretty straightforward and self-explanatory. The only thing that I would maybe point out is that there's a good chance that 50%, it could actually be slightly more than that, because I would feel that the 6 gram per liter traditional systems, due to building the byproducts, the viscosity is going to significantly increase. So I think actually it could be more beneficial than just 50% at minimum. So deposit characteristics are pretty straightforward. Typical systems that we would see with a mid-FOSS, 5 to 8%. You'll see some systems 6 to 9, 5 to 8. They all fall within the range as designated as a true mid-FOSS system. And the hardness and wears will be typical of traditional systems, as Helmut stated. We wanted to make sure that the performance and the characteristics and properties of the coating and has no detriment and meets what we're traditionally need for the customers and the end users and meeting different specifications. So here's your operational conditions. Again, it's 3 gram per liter and 20, which are kind of common for the nickel and hypo. Temperature range are similar to what you're used to using. pH range is similar And plating rate is traditional of a true mid-floss of 5 to 8/10 mil per hour. So that's common, and then with the similar loading range that we are familiar with, and what Helmut had just mentioned about the HP version as well. So pretty similar to traditional 6 gram per liter mid-floss systems. So here's some of the performance as well, just to extrapolate on a little bit. There's mention of the Endplate AL100 as far as a barrier coating to help expand the aluminum metal generations, so that we had talked about previously in the strikes presentation earlier. So as far as your coverage, at 10 metal turnovers, 6 mil per square foot per gallon would be your coverage, and at 16 MTOs would be 9.6 mil square foot per gallon of your coverage. So brightness rating. So this is what they came up with, a graph to just kind of document and control how the brightness was and the consistency of the life over the trial. And it shows that it's very consistent, and that's one thing that we've seen and we're learning with these ELV systems, is that they tend to tune their brightness better than some of the traditional the legacy cadmium systems. The cadmium systems may have been a little brighter at the start. I guess this would be based on probably 10 would be the ideal. But as we know, within that first turnover to the cadmium systems really lost that gloss or that brightness. So you kind of lose some consistency for your customers and for the end users. So something that's really been beneficial to these ELV systems, especially the system was based off of our NiKlad ELV 847 system, which is a benchmark process for us and our brightest in our portfolio. Based on gloss testing, so it's proven data that it is the brightest, basically we feel, in the industry, and that's what the system's based off. So as you can see, the brightness is consistent, so you can really give a consistent looking part to your customer, depending on no matter what the age of the solution is. So here's a chart of plating rate, which you had seen similar to what Helmut presented for the HP version. And there again, you can see that this was ran pretty much 83 to 88C, which is around 182 to 191F. And there, as Helmut mentioned, it's a good temperature rate, but it was not pushed, and there's still room to take it higher to 90, 91C if needed towards the end of the life. But we still had fine plating rate of 20 microns, which your range of 15 to 20 is going to fall in 0.6 to 0.8 mil per hour. And pH was maintained pretty regularly, just shy of 5.0. So as Helmut had stated, there's still room to even push it if we needed to do that. But we got pretty good rate at these levels. So here's the drag out that Helmut went over. So it's pretty much is exactly what he had spoke about. So I'm just going to skip over this one. And then the cost slide here. So Helmut had talked about that we do have a comparison tool. So that we do have cells that can be populated. And there again, like I said, we can work with our account managers for individual customers and do comparisons to whatever traditional system you're using currently. So yeah, there's many cells that can be populated and really take a good look at based on what is the makeup percentage, the replenishment percentage, how many metal generations you currently get, the drag out scenarios. So it's a great tool to elaborate and show this in a very transparent way that Helmut had mentioned. And here's just an example of some parts and pictures of the brightness of some parts that were plated at the trials. Sorry. So the customer experience, we actually did 4 studies on this, so it's been thoroughly tested, and we saw a very good level of stability. And there again, like I said, this bath is based off of our benchmark process, NiKlad ELV 847, which is one of not only our brightest systems in the portfolio. It is also one of the most stable that we have in our portfolio as well. So that's what this is based off of. So you saw that we saw the plating rate that we would expect with traditional 6 gram per liter, which was consistent. And you can see that they ran numerous substrates, which we always try to thoroughly test. It's hard to run it on everything, but they were able to hit at least 4 different types of substrates. And obviously it's our goal to always to test and prove it out in barrel and rack, which they were. And they were able to trial it on a very low loading, and then definitely some good mid to mid-high loading, pushing 0.5 square foot per gallon. So that's good. And also the ranges, anywhere from very thin flash, 0.2 mil to up to 1.3 mils, definitely over 25 microns and plus. So was able to run in the stainless steel tank and with an anodic protection, and perform very well. So this is just a summary of a lot of the advantages and benefits, and we talked about all of those pretty thoroughly. So I'm not going to elaborate too much on these. They're pretty self-explanatory, and I wanted to just end so we can help answer any questions that people may have, or they can email us separately, as Rob said. So with that, I'd like to thank everyone for your attention, and stay safe, everyone.
John, Helmut, thank you very much. Great session on the ammonia-free strike and low metal electroless nickel systems. We do have one question that's out there. The question is, what is the typical metal turnover increase that we would see from an EN process solution when a electroless nickel strike is used?
Yeah, maybe I can handle that question. I mean, the number on MTOs in general, it really depends on the thickness that you plate and how many surface area that you process through the solution. John had some numbers on the slides for how many milligram would dissolve. But basically, when you compare a single zincate towards double zincate plus EN strike, it's about 1/10 of the buildup of zinc. So that's really important. Basically, with an EN strike, you get to almost to the normal solution lives that you would otherwise expect on steel. While otherwise, traditionally, if you do only a single zincate, very often after 3 MTO or somewhere maybe a little bit higher, you would see some compromise in the adhesion or in the performance of the coating, so that you would need to switch to steel or either have a new solution. So for everybody who is only processing aluminum, it's very much recommended to use an EN strike. I know not all lines can accommodate an EN strike, but those companies who do a lot of aluminum work, there it is usually very, very commercially attractive also to apply an electroless nickel strike, and the lifetime of the EN can be as increasing by up to factor 10 sometimes, so that the aluminum or the zinc contamination doesn't really play any role anymore for solution life.
Yeah, thank you, Helmut. And the only thing I would add to that is, yeah, it's sometimes it's individualistic to what type of system it is and how it's formulated and chelated. So that all comes into play as well, as far as whether some systems might get 3 metal generations or 4 or 5. So there will be sometimes some kind of a range based on how the system is formulated, and especially how it's chelated as well. So that comes into play as well.
Great.
Yeah, I would like to thank everybody for joining here, and I hope you did enjoy what John had to present here. And Rob, you have the final.
Sure. So that's really it for the session. Again, John, Helmut, thank you very much. Very informative session. And again, for the additional questions you have, please contact John Pawlowski directly, and he will respond back to you via email. Have a great day, everyone. Stay safe, and we'll see you next time.